Hi all. Today I am going to discuss about Lenz law. There is some confusion among students on how to take the direction in EMI. Now basically what is this Lenz law means? It is first based on the principle of conservation of energy. It is based on the principle of conservation of energy. It states the direction of induced current will be in such a way that it will oppose the change that produced it. Now let me explain this with an example. Now first of all we need to understand the basic concept that why induced EMF is coming. Suppose you take a current carrying conductor. Okay, right now I will take some counters. I will take a coil here. Okay, now basically what happens, we'll put a counter for the flux here and the current here. This current is what you are supplying. You are supplying this current, okay, which is in your control. So initially when current is 0, there won't be any field around it. We can find the direction of the field by using our right hand thumb rule. If this is the conductor, we have to hold it like this. This thumb will indicate the direction of the current, and these fingers which are curling will show the direction of the field. So here the fingers will go inside, so the direction of field will be cross, which is into the board, into the plane, and on the left side it will be out of plane. So initially when current is 0, there is no field associated with the moving charges. So what happens is flux will be 0. Suppose you increase the current to 2. Now some lines may pass through the coil. So let us say some 4 lines are passing through that, magnetic field lines are passing through that. Suppose if you maintain this same current over a period of time, then the associated flux will not change. Suppose at 10 o'clock you are sending 2 amps, and between 10 o'clock to 10:05 you are sending same current, so same number of lines will go. So there won't be any associated change in the flux, there won't be any change in the flux in the coil. But the moment you start changing the current, what will happen is these lines will keep on increasing, because you're increasing the current, that is di by dt. Now it is not equal to 0. You are increasing the current. Let us say you are increasing current or decreasing the current. So some flux change will happen inside the coil. This will give rise to a induced EMF, an induced current in the coil. Okay, so here induced current in the coil is due to this di by dt only, which is not equal to 0. So the associated B is changing here and the flux is getting changed. Now we have to know what is the direction of the current that will come in this coil. So for that, what we are trying to say is, suppose we will take the case I is increasing. This is, current you are increasing in the coil. What happens is this cross, which is due to I, gets stronger and stronger, right? Stronger and stronger. So when this gets stronger and stronger, what we have to do is we have to pass current in this new coil in such a way that it will oppose this change. That means, so if the field is like this, if you create a field which is like this, then this will oppose this. If you try to understand in 3D, see, this is x, y, z. So right now the field lines are in this direction. are in this direction. I want to oppose the change. That means I should create a field line in this direction. This will oppose the change. Okay, so I should oppose the change. So I should select my current direction in such a way that it should produce the field in this direction. So suppose if I say that current is passing in anti-clockwise direction. Okay, so what will be the field? This is the current which is going like this. I'm holding the current. You see the fingers, they're pointing towards you. So if I take the current direction as ACW, the associated field will be like this. So this is reducing the effect of this, which is following the Lenz law. So the current in the coil will be in the ACW direction, anti-clockwise direction. Okay, let us take another case and quickly see some another case, just for understanding. This time what I will do, I'll take the coil here, I'll take the conductor here. Now I is decreasing. Okay, so what will be the direction of induced current? So induced current will come into this. Induced current will be developed in this. So because I is decreasing, the flux will change. See, we have to ensure that the flux should change. So here the associated flux, is changing. First of all, we have to ensure that. Now because I is decreasing, first of all you find out the direction of the field because of I. So it is like this. So the thumb is indicating in the direction of current. So my fingers on the left side, they are like this. So the direction is like this. Okay. Now this is also decreasing because the current is decreasing. So what I should do, I should enhance this value. So I should select the field, I should select the direction of current in such a way it should give a new field. See, you know that suppose if I take a direction like a clockwise, if I take clockwise, suppose some clockwise current is there. So clockwise current, see how the clockwise current is creating. The clockwise current is creating field like this. Okay, clockwise current, yeah, clockwise current, if you try to hold it like this, so they are curling inside, the field is like this. So this field, is it enhancing this or it is reducing this? It is actually reducing this. So you should not select this direction. You should take anti-clockwise. If you take anti-clockwise, what happens? Anti-clockwise, you will get a field like this. Okay, so already this is decreasing. So you are adding to the system some more dots. So it is increasing. So here also the current direction will be anti-clockwise direction. So opposing the change actually means if I is increasing, field should decrease. And if I is decreasing, then field should increase. This is exactly the meaning of that. Okay, so thank you very much, and if you have any doubts you can send me on my WhatsApp. I'll try to answer them. Thank you.